Hi, I'm Onas Bolton, founder and CEO of Octet Scientific.
And I'm Emily Dickens, Chief Commercial Officer at Octet Scientific.
And welcome to Aqueous Energy, the show featuring pioneers shaping the next wave of aqueous battery technology.
Our next guest is Dr. Adam Weisenstein, Chief Technology Officer at zinc-based battery manufacturer AEsir Technologies.
We'll discuss how AEsir is bringing energy storage with safety and durability to the Department of Defense, how their raw materials spin-off battery-grade materials is changing the supply chain equation, and a lot more.
One great tidbit you'll hear: what happens when you fire live ammo at your energy storage application. Let's go to the conversation. You know AEsir is a zinc-based battery company. Can you dive into why you focus on zinc?
Zinc, first of all, is everywhere. As we know, there's, it's abundant, it's domestically produced, very high specific capacity. Zinc's safe, it's recyclable, and it's inexpensive. So all of those things combined, it just, really it screams at us to combine that with another, inexpensive, safe material, whether that's nickel. There's a lot of other technologies that are, let's say, lithium based with zinc that makes it safer. There's sodium, there's, many other silver zinc over the years. So what we did is we really wanted to be a zinc based company, meaning that we focused on a lot of different zinc chemistries over the years, but we really focused at the end of the day on nickel-zinc. Nickel-zinc is going to fit really in between lead acid and lithium-ion, but it's going to give you the added benefit of safety. It's environmentally friendly, recyclable, inexpensive, long cycle life, and high power. So all those things combined, that's really where we see the value add with our nickel-zinc flagship chemistry. And for DoD applications, it's really a perfect fit for the application that needs more power or more energy than lead acid can supply, but the added safety, right? So we want to make sure that, our DoD applications, that the soldier is safe. That's not going to ever cause any sort of added damage from electrification from our batteries. And so that's where it fits really nicely in the DoD application.
Can you speak a bit more about how these projects are useful for the military, what you're kind of doing with them today, as much as you can expand on?
Yeah, I mean, we've worked with all branches of the military. And I think it comes down to the same thing that I talked about, is needing more from the battery, but wanting it to be safe at the same time, right? So not only do you need the extra power, the extra cycle life, higher watt hours per kilogram, higher watt hours per liter, than a traditional lead acid battery, but you need it to be safe. You need a domestic supply also. So I think that's what most of what the last couple of years, I would say, of R&D is. It's to make sure that we have a domestic supply for all of our materials within the battery. If that means that we have to go out and secure the base mineral and go through refinement to get that to a battery grade type of material, that's something that we are taking on. That's actually one of the reasons why we started battery grade materials, is to make sure that we could secure those critical minerals and turn those into a battery grade material at the end of the day, and then also be able to recycle the battery back into that battery.
Yeah, that's great. Yeah, it's really interesting what you're doing with battery grade materials. I mean, like you said, kind of approaching the scarcity that other technologies may find with their materials, but being able to source yours domestically. Can you talk more about battery grade materials, how it got started, where it's at now, and how it's related to AEsir?
Yeah. So as we were going through scale up, once we really figured out, where are our applications, not only DoD, but then when we're talking about data center applications, and we all know, the data center market is huge, right? And growing every day. So when we looked at our gigafactory, and what that would require once that gets up and going. And whether that's producing 1 gigawatt hour of energy, or we're talking 6 or 7, most companies that we were working with weren't able to supply the active materials that we needed. And they weren't willing to grow with us at that point in time. So what we wanted to do was make sure that we could, again, secure, whether it's nickel or zinc from the mines, and be able to refine that, whether that is third party, domestic third party, or whether that's internal. We needed to make sure that that was taken care of before we went any further, down the road of really producing that many batteries. And then what do you do when you produce all those batteries, right? There comes a point in time where you have to recycle those. You have to know how to recycle them. What's the plan for recycling those? And what's the cost and what's the benefit behind it? The great thing about aqueous zinc batteries is that they're easily recyclable. It's a process that doesn't require much energy whatsoever, not high temperature process. It's really, at the end of the day, it's a simple, water-based process for recycling those materials. So now that we are able to secure the materials, we know how to, again, refine those, synthesize those into battery active materials. We have this 360, life cycle taken care of. And that's why we started battery materials, is we needed to make sure that we understood that completely, that we understood from the R&D perspective to the business perspective, and make sure that was completely handled from our side while AEsir grew.
Yeah, I think that's really good, because there are a lot of batteries that are built with simple and available materials, but the actual grade, the actual form of the material might be a challenge. And we're seeing that there are, I look at it like, for batteries kind of across the board, it's like, manufacturing scale up is where the real kind of valley of death kind of looms for battery companies. And for a lot of companies, it's because they have to make all the components like brand new. But I think it's really telling in a space where the ideas that the materials are simpler than where they might be in other batteries, that a company like AEsir could just kind of become vertical like that. It's like, I don't think a lot of battery companies out there are going to try to make a brand new battery and then also be able to set up become its own supplier at the same time, unless the materials were accessible and scalable and available. I think it's a real testament to the kind of material simplicity maybe of the battery, that maybe the grade wasn't available, maybe the exact form of the compound wasn't available, but you can do that yourself in a way by setting up battery grade materials. It's like, I think it's a real testament. And also what you're saying about the recyclability really resonates with me too, because we're seeing in the lithium-ion world that recycling is kind of an afterthought, or is a later thought at least, that it's like, well, now we got to solve this problem because it wasn't there from the beginning. They were shooting for high performance and they got there. Now what do we do with all these old batteries? And there are a lot of great companies doing a lot of good work to solve that problem. But if you look at some of the most widely recycled materials in the US and world already are things like zinc, and iron, and things that are not expensive materials. They're just easy to recycle, and that's why they kind of enjoy this kind of circularity already. So, it's easy to understand how this is all going to work out once these batteries are at large scale. It's like it's already easy to recycle. I think of these metal batteries as like almost kind of recycling machines. It's like you're kind of redoing the metal every time you charge the battery. It's like they almost kind of do that internally anyway. So, it's great that you're seeing this kind of circularity from the very beginning, and building it up with the company, not as like an afterthought for some other.
Exactly. And the great thing about nickel-zinc, and I think a lot of the aqueous zinc chemistries is, in a way, they are simple, right? And I think you were alluding to that it's one of these processes where, manufacturing wise, right? We can talk about that, where you don't need dry rooms, you don't need glove boxes. These things, you can take them apart; they're not going to explode. For instance, we actually one of our larger batteries, we down in Joplin, they took them out and they did some bullet penetration tests. So they shot it about 3 times, it had the same charge voltage for over 24 hours after it was shot, right? And then they put a lithium ion next to it and shot it, there wasn't much left. So uh, again, I know that's the safety part, but I think it comes back to, this being aqueous. It's simple, so it's easier to recycle, and the processing itself is fairly simple. You can use lead acid equipment for manufacturing for the most part. And especially what we've done here is we made sure that when we went through beginning 12 years ago, we looked at it as, hey, we have this great technology, but is it going to be scalable?
Mm-hmm.
Can you go and use existing equipment to manufacture this? And if not, okay, well, that's just another headache, right? We would have to, go spend our engineering hours, our R&D hours to make that possible. And instead, with some minor tweaks, we can use lead acid processing equipment. And now we can just, use our engineering hours for specific application and R&D hours for improving the chemistry itself. So, from the very beginning, I think that was I think the right path that we were able to take. And for most aqueous, I think zinc chemistries, it's fairly simple. I think what's great about what we're doing with battery grade materials is, not only looking for where can we get this material from, whether it's domestic or overseas, as far as the nickel or the zinc, but we're also looking at, okay, what's here, what are our domestic sources for nickel, and what we found is that there is a lot of nickel here already, right? And we're not talking about recycling from lithium-ion or recycling other batteries. We're talking about what's there from mine tailings, and there is quite a bit of nickel and cobalt in these mine tailings. And, that's something that we are working with some other companies on, to hopefully be able to, extract that nickel and some of the cobalt. There's other, reclamation projects where there's a lot of nickel in the ground that we can extract. And so it's sort of thinking outside the box. Okay, where can you get this other than just the mine? And there is nickel mines here too, and so I don't want to discount that. But, I think you have to look outside the box a bit here as far as domestic supply goes.
Yeah, and I mean, especially, it's undeniable that we're here talking about alternative chemistries to lithium, but lithium is a huge world-saving chemistry. It's fantastic. There's no denying where it's going to go, and it's going to need materials too. And any sort of tailwinds or synergies that can be gained by having some of those same kind of supply lines set up in the U.S. I think everyone's on board with that. I mean, despite all the political shifting of gears in the last year here, everyone's on board with the idea of localized domestic manufacturing. Having these things be more broad. So, we don't always need to think of it too as lithium chemistries versus alternative to lithium. It's like, there's room for everybody, and I think there's need for all these different things. And so, I think the idea of, we always talk about like resources and materials, and I think like we live in a really big country. we have a lot of space, and there's got to be a lot of stuff underground there that we could be using. And as long as we're doing it responsibly and all that.
I think that's exactly right. Yeah, I mean, when we diversify our electrification, with these different chemistries, also we lessen the load, right? That we need for specific materials for lithium ion. So, it's not about ever eliminating it. I mean, I want my cell phone to fit in my pocket, and that's not something that I'm going to be able to do right away with any sort of aqueous zinc chemistry. So, it's about finding the right application, about, I think, diversifying our battery chemistries and really what's accepted for these markets where it fits. And, there is a lot of markets out there that don't have to be dominated by lithium ion, and there are some that have to be right now. We don't have a great alternative, and it's been wonderful for us. So, as far as lithium ion goes, I just think that if we are able to look at different chemistries, different materials, then, it makes it easier. on everybody to make sure that we can secure those materials and make sure that we have, the right amount for the right applications.
Yeah, that's great. And I know in Joplin, you recently announced you're expanding your facility there. Can you speak a little bit on that?
Yeah, definitely. We started the expansion. I was able to see, some of the early on progress just a couple weeks ago when I was down in Joplin. Just actually today, we had a video that was uploaded. If you're on LinkedIn and you
Hmm.
follow me or AEsir Technologies, you can see the new video. Quite a big expansion. So we needed that. Our DoD demands. We have to scale up at this point. We have to start producing more batteries. We have to get these lines that I was talking about earlier. Some of the manufacturing lines, that use existing lead acid type of equipment. We need to just expand those lines to be able to meet the demand right now.
Yeah, that's really exciting. Great to see that demand is rising for, such a great technology like yours. And I guess what you mentioned, it's a lot easier to put up manufacturing for this technology. Can you explain some of the key differences? You mentioned dry rooms, but how, what does it take to put up this kind of facility?
Yeah, I think there's advantages to this sort of technology compared to some of the other technologies out there. And like you talked about, there is dry room, glove boxes, that sort of thing. Formation equipment, formation's quicker for these than, let's say, a lithium-ion battery. So that means you can scale that part of it down. It's traditional, type of equipment that you would see just about anywhere in a lead acid type of manufacturing facility. As far as HVAC goes, it's your typical type of HVAC, right? There's nothing exotic about it. Just making sure that the whoever's working the line is comfortable at that point. There's nothing that's really needed as far as humidity control, temperature control. Those sort of things are kind of taken out when you think about this sort of technology.
Yeah, that's good. I mean, I would imagine that leads to a lot more kind of robustness in terms of quality control. If the batteries themselves aren't as sensitive as others might be, I think it eliminates a lot of, they're just a lot more rugged in performance, but also in manufacturing. So they're not the kind of prima donna, maybe that lithium ion is. High performance, yes, but you got to keep it real happy.
Agreed. And I think, to add on that, it's a technology where for different applications, it's fairly simple for us to turn the knob for this. As you would say, it's a technology where, let's say, our electrodes, our cathode or our anode thickness could vary, from anywhere from 100 microns to 1,000 microns, and we're still able to get very good performance. Of course, any of your C rates are going to change and some of your power performance, but it's some of those things where you can vary your electrodes dramatically and you still get great performance out of it. So that's one of the advantages here, right? And it's that simplified, chemistry, like you were talking about, where it doesn't have to be exactly, let's say, if it's 150 microns for the electrode for it to perform properly. These are things where we can dictate, what that capacity is going to be at the end of the day, dependent on the application, and of course, cost of the battery. That's going to vary greatly on your thickness of your electrodes, how many electrodes, your inactive materials within your battery. So that's one of the advantages of the aqueous zinc technology, especially nickel-zinc.
Yeah, and I'd believe, maybe you can validate that it would make it easier also to just integrate changes, feedback you might be getting from pilots you have out there and the kinds of work you've done already with the DoD and others. It's easier process to change than one that's very, very tightly controlled and, has a much tighter tolerances. I'd imagine, there's a lot more variability you can tune to performance, batches at a time.
Yeah, absolutely. Absolutely. And for us, we perform, DPAs, the destructive physical analysis, on just about everything that we receive back. And in R&D, it's every single cell that is cycled. We go through that analysis. That's, everything from, observations during teardown to XRD, XRF, SEM analysis, those sort of things. We take in for every battery that we can. So then we can make those tweaks, like you were talking about. We can make those adjustments, and those adjustments are quick for us because it is, simplified in many ways. The equipment's simple, and the chemistry itself, like you said, is fairly simple, so we can make those changes.
Yeah, that's great. It kind of takes me into my next question. I mean, you have a great product, you have great demand for it. So where are the products going next for AEsir in terms of R&D, beyond, improving nickel-zinc and beyond? Where are you looking at?
Yeah, I think, to begin with, it's going to be, where do we go with nickel-zinc? Right. And for me, I think at the end of the day, this is just the beginning. As you know, R&D funds for aqueous zinc chemistries are not what they've been for lithium-ion in the past. And I think that as that grows, as popularity grows with the zinc-based chemistries, it's the tip of the iceberg, right? For a lot of these chemistries. I think nickel zinc, to a point, I think there's a lot of capacity that's unlocked, power that's unlocked at this point. It's just, or can be unlocked through R&D and really through what we're doing right now. All of the different changes that we're making are leading to greater performance. That greater performance of course leads to more R&D money that's coming in for it. So again, it's tip of the iceberg for nickel zinc. And I think that's just going to lead to, really more market penetration into different applications. But there's a lot of other chemistries out there. For us, we've worked with lithium-zinc, which is also a great chemistry. It's safe, uses a lot of the, traditional lithium-ion intercalation electrodes and long cycle life, inexpensive. There's also sodium-zinc that I think the future is really bright for. That would be a technology that, through our calculations, could be anywhere from 2 or 3 cents for levelized cost of energies. There's, I think, a lot of space for these zinc chemistries, right? Whether the thing is that they're all different, right? It's like any other battery chemistry out there. There's specific applications that are great for different battery chemistries, just like lithium-ion.
What do you think we need to get to those kind of next levels of zinc batteries? Because I think that a lot of the zinc batteries we see being commercialized these days, they're chemistries that have existed in some form. Like, I think Edison had like nickel zinc patents. There's like,
Yes.
So, but it's really exciting to hear you talk about something like sodium zinc, which we really haven't encountered yet. But I mean, how do you see us getting from today's zinc batteries to kind of, the next stages, next new chemistries, new applications? What are the barriers there?
Yeah, I think, well, number one, there needs to be more support. I think from whether it's in academia, whether it's in industry, having that funding for these sort of chemistries is going to drive it, right? And then past that, past the sort of basics for these chemistries, it's it's can we, let's say, go to a higher voltage with an aqueous chemistry? Those sort of groundbreaking things. Is it, let's say for nickel zinc, are we able to get 1.5 electrons out of the nickel hydroxide instead of 1? There's a lot of things that we can do with these chemistries to make them, whether they're competing with lithium ion, or whether they're, better for a different application. But there's so many different ways that we can go about this, that really it comes down to, funding at the end of the day for both, us in industry, and then in academia. And, we rely on a lot of that for, in academia, to make sure that we can, where a lot of the fundamentals are researched. That becomes a little bit difficult in industry when you're trying to produce a battery for a specific application at the same time that, you're trying to, overcome some of these, fundamental chemistry questions.
Yeah, I think historically we've seen a lot of companies in the battery space become real expert at selling the battery for the application in the market, and they get kind of, cloistered into the markets that they know, and really kind of spending more time maybe fine tuning what those batteries, those batteries being better for that application rather than branching them into other fields. I think lithium's a little different because maybe the batteries are just a little more smaller, modular. I don't know, but I agree with what you're saying, that there are chemistries like a lot of the ones that are based on zinc that we could translate some of the discoveries we have in certain chemistries to other chemistries that are based on the same maybe anode or something like this. And there's certainly going to be more applications for these kinds of batteries, but it will require some broad thinking, I think, to kind of establish these different chemistries in different places.
Yeah, definitely. And I think a lot of our breakthroughs in R&D have come from, different battery chemistries. Looking at how even from lithium ion to, let's say, like a nickel cadmium or nickel metal hydride, or different, maybe silver zinc. Looking at how they were able to, let's say, either stabilize the zinc electrode, or get nickel electrode, or maybe stop gassing at higher temperatures, those sort of things. We're able to look at the research that was done in a lot of the different chemistries and then apply it to ours. And we that's what we do first of all, is look, okay, what's been done in the past, right? If we come across an issue or a problem that we need to overcome, what's been done in a similar chemistry? Okay, what's been done in all battery chemistries? And then look, okay, is that a product that we can actually, first of all, implement fairly quickly? It makes sure that it doesn't require necessarily a large change to manufacturing, or, to the battery itself. Is it domestically available? And then, is it inexpensive? Those are kind of the things that we go through. And a lot of that, you get an idea, and then, okay, where is this available? And sometimes it's a food product, right? Or it's it's some sort of additive in food, or in the medical industry, where a lot of these things come from. And so I think you have to look outside the box. You get the idea from things that are similar, and then you look outside the box for materials that actually work.
If you were to kind of pinhole or choose one specific area of support, where do you think a lot of focus should go towards for zinc batteries in general?
Yeah, mostly all of it, but I would say, typically for any sort of zinc-based chemistry, it's typically on the zinc side that's where your failure mode is going to happen, right? I mean, zinc tends to move where it wants to. You try to stabilize it as best you can, but at the end of the day, it's there's dendritic growth, there's migration, there's islanding, passivation, all those sort of things. I mean, that's common throughout all batteries, but especially with zinc. And so that's where most of, I think, the R&D money is spent, but it's well spent, I think, in a lot of ways, because that's where it needs to be focused. And what you guys do with electrolyte additives too, because that affects the whole entire battery. So whether we're talking about the cathode, the anode, the electrolyte is going to affect everything. That's, it could be, it can affect it at high temperatures, low temperatures, your hydrogen evolution reaction, your oxygen evolution reaction. all of those things, along with, the wettability, I could just keep going on all these things where electrolyte matters, right? And that's one way of unlocking our higher voltages that we can go to with an aqueous chemistry. Eliminate a lot of the gassing that's associated with those higher voltages, stabilize the materials for longer. So I would say, between electrolyte and zinc, and really stabilizing the zinc anode during cycling, those are probably the biggest two.
Yeah, it's a tough question because you tweak one thing, you change a lot of things within the battery. It's not as straightforward as yeah, as oh yeah, we just fixed the zinc and everything else is behaving the same as it was. So I know that was a challenge, but um yeah, very interesting.
Yeah, we encounter the same thing. I mean, it's a new space in a lot of ways, and everything is changing all at once. And so we've definitely done work and had things change and adapt. And it's such a complex system that it doesn't always work that you solve each problem independently. Like, okay, this is done, now this is done, now this is done. It's like, well, every time you make a new change, it kind of rewrites what was done before. And so it's more about just a lot of broad iteration, I think, than just like a linear series of problems to solve, because there's too many things happening and there's too many variables really, across the field right now. I think it's kind of a blessing and a curse that batteries like zinc batteries, have so many chemistries, so many markets they could go to, so many possibilities, so many form factors. What's kind of a kid in a candy store a little bit about like all the things these batteries could do, but then you got to start trying to do them and making a lot of decisions, and the variety and variability, also means that there's a lot of work to be done to kind of nail it down exactly how you want it. But the
Exactly. And then
possibilities are endless.
the application's gonna dictate a lot of that too, right? So, if we're running one of our batteries at an 8C rate compared to, C over 3, it's a much different issue.
Well, one thing that stuck out to me, and this is kind of going back to the previous topic about battery grade materials, is we've seen a lot with some of these uh, alternative to lithium ion chemistries. A lot of times they have to kind of build up their own supply chain. Do you plan on leveraging battery grade materials for, selling them to other battery companies that might be up and coming? Is this, in that plan, or is it really just, we need to have our own supply chain and this is the best way that we could think of to do it?
But yeah, I think eventually that would be great,
Hmm.
right? First of all, we want to focus on our needs.
Hmm.
Um, and then secondary to that would be, okay, these different, whether it's a byproduct, let's say, or there's some materials that we would get from recycling that we could sell into other industries. Um, we're also looking at, new materials, whether those materials are you know, whether it's going to be 100% committed to our battery or not. I think at the end of the day, that could grow into, a much bigger company where we're supporting a lot of these different chemistries because of the advancements that we're making. Um, it's one of those things where we're putting in the money for R&D for this knowledge from, let's say from our consultants, from, all the work that's been done. And, that could definitely grow into, like you said, us helping these other companies out, us selling these materials that we had to, you know, spend the money to develop
Hmm.
at that point, because it was just needed for us as that as we grow into this larger battery company.
Yeah, and I think it's a part of the being in such an early space with a lot of things changing, and there will be some things that will become kind of standardized in different parts. And something that we talk about a lot on our side is that it won't take many of these early stage battery companies to succeed before there'll be lots of copycats and competitors and licensing. And it's like the future is just so big for battery technology, and everyone's really really excited about alternative technologies. And I think a lot of people, a lot of money maybe, are waiting to kind of see, well, who are going to be the real winners coming out of this. I think when we talk to people about diversity in energy storage, and like lithium can't do everything, and even lithium and sodium, people generally agree. Like it's not, you got to have the right battery for the right application. Batteries are becoming a bigger deal than they've been in the past. So it's not just going to be, we have two battery chemistries and we just use them for everything. It's going to be like different markets will have different chemistries. Everyone's kind of on board with that idea, but they're really kind of waiting to see which ones are going to be the winners in these different areas. So, as soon as, Acer's batteries, start to, really break out, there'll be lots of competition. There'll be copycats and people wanting to license, and who does your material? They'll go to battery grade materials. And so like, I think things can kind of spill over the edges of the dam pretty quickly here once there's real footing, once these go from, pilots, demos, early adopter kind of customers to like, now people trust these batteries. And once they trust them, I think things will move really quickly, and we'll see, a proliferation of manufacturers and technologies, especially when they can use existing lead acid manufacturing or this sort of thing, where you don't need to kind of totally greenfield the new factory to make these batteries, because a lot of that's, yeah. And then you guys will make a lot of money selling battery grade materials.
Great. Well, say within the next 5 years, Aqueous Battery Technologies get funding for R&D, there's progress being made. What would you love to see realized, not just for Acer, but for the field overall?
Yeah, I think for Acer itself, we're making so much progress that, a lot of things that we're doing today, you'll see in that 5-year time frame, right?
Mm-hmm.
As we know, everything that happens in R&D, takes at least a couple of years of just, first of all, scaling it up, and then, going through the battery trials, making sure that we're getting the performance that we've seen in small scale, and then, scaling that up to the large scale batteries. So a lot of what we're doing today, of course, I want to see that implemented in batteries in the next 5 years, right? And that's mostly on the nickel-zinc side. And then for us personally, here at Acer, I want to see these other chemistries that we worked on. I want to see the let's say lithium-zinc, or whether it's sodium-zinc. I want to see that scale, right? It might not be something that's ready for prime time, but it's something that we're excited about. We think that those are also, I don't like to say game changer, but those are also other chemistries that I think will make a difference, right? So within the next 5 years, I would like to see that taken to the next level, and getting in those chemistries into our larger cells, right? So that's kind of Acer, I would say. Battery grade materials, it's more about, the next 5 years, making sure that we have these materials. We have a domestic supply of these materials. Everything's put in place. We know, how we're getting the materials, and what the cost is. Also recycling, making sure that we have those recycling facilities up and running and ready, right, for all of this. And then overall, I think it's just market acceptance. And Onas, you talked about that, where these aqueous zinc chemistries, what we need is just market acceptance overall, right? That's going to help all of these different chemistries out. Once customers feel safe, and they understand that these will be reliable, that's a win for all of us. And so within the next 5 years, that's a lofty goal, right? For a lot of different chemistries. But any sort of market acceptance, I think, would be a big win for the aqueous zinc chemistries.
Well, it seems like getting the stamp of approval from the Department of Defense would be a great way to build consumer confidence, I think.
Yes.
You're probably on the right track there. We've heard that same message from a lot of people. And it's honestly one of the reasons we started this series, is like to shine a brighter light on these technologies, because for good and bad, we live in the battery world. There's just so much hype, and there's articles, every discovery is a breakthrough and everything's going to change everything. There's a lot of noise, and one thing we wanted people to see was that despite all that, these are batteries that are being manufactured, installed, and used in the field already. Like, you have a factory in Joplin where these batteries are being made and they're being used by the military and others. these aren't, just pilots. These aren't laboratory projects. These are real batteries, and they're out there. And we want people to see that because, a lot of times, batteries don't get a lot of love. They kind of work quietly in the background. So, I think there will be a turning point. How sharp the turn is, I don't know. But where all these technologies go from, it'll be cool if that works, to, oh, no, they work and they've been working for years. And now it's time to, now people will feel like they really do have a serious alternative, to lithium-ion technology in different applications. And it's not about uncertainty, but confidence in these kinds of things. And 5 years seems like a pretty realistic window to me, given what's out there already. And like I said, especially if you have like the Air Force, giving you the thumbs up, it's like, okay, if these are mission critical, they're probably good enough for your whatever domestic application too.
Yeah, definitely. And these are large cells, and I think you were talking about where a lot of times you'll read about the next breakthrough, and it's a coin cell or a button cell. And, these are large, very large batteries that we're producing now and testing right now. And, really the simulating a lot of those environmental conditions that we'd see in the real world with these very large batteries. So it's progress, I think, overall, to demonstrate that these batteries work, these chemistries work. And they work well for these applications.
Well, that's a wrap on today's conversation. Thanks to Dr. Adam Weisenstein, Chief Technology Officer at AEsir Technologies, for joining us. And thanks to you for tuning in to Aqueous Energy, the show featuring the pioneers shaping the next wave of aqueous battery technology.
If you like what you heard, please be sure to like, subscribe, and forward to a colleague who might find it fascinating.
Aqueous Energy is a production of Octet Scientific, a company helping aqueous energy innovators deliver their most competitive batteries yet. We've helped companies boost their capacity 20%, increase efficiency 10%, and doubled their operating life, all without a model rebuild.
Want to learn more? Head to the link in the show notes to visit Octet Scientific online.
Thanks for joining, and we'll see you again in the next episode.